These two trucks, the 5-ton and the 2.5-ton, are basic in all Army transportation. Most of these trucks are being equipped with multi-fuel engines. When vehicles are limited to a specific type of fuel, field supply may sometimes be a problem. This problem is eased with a multi-fuel engine. Its internal design features allow for operation with many types and grades of fuel, even liquids as different as peanut oil and alcohol. For the most efficient operation, however, choose one of these four. First choice is diesel fuel. Next, CI, compression ignition fuel. Then, JP4, jet petroleum. And fourth choice, low-octane gasoline. This may be considered an emergency fuel. A great advantage is that when changing from one type to another, a compensating device on the injector pump automatically adjusts to ensure maximum engine power. This film will cover the injection system of the LD and the LDS 465 multi-fuel engine series. LD stands for liquid-cooled diesel. This is a naturally aspirated engine, that is, air enters the combustion chamber under atmospheric pressure. LDS indicates liquid-cooled diesel equipped with a turbocharger, a blower which uses the energy of the exhaust gases to compress air into the cylinders. Multi-fuel engines are no more complicated than the long familiar spark ignition engines, but they do require more responsibility in operation, maintenance, and repair. We will show you what the real professional must understand and look out for. The principal units of the fuel injection system are the fuel supply tank with an in-tank pump, the filters, the primary filter on the frame of the truck, and the secondary and final filters on the engine. The flame-type manifold heater consists of an ignition unit, an electric pump, and the heater element. This is the fuel supply pump assembly. The fuel injector pump and hydraulic head assembly, the governor, the fuel density compensator assembly, the advance unit, and the fuel lines from the hydraulic head to the injector nozzles of the 6 cylinders. The lines from the hydraulic head to the injector nozzles are made of soft annealed steel tubing to carry fuel under high pressure. The return lines from the nozzles carry unpressurized fuel to the tank. They are plastic lines. The elements in the hydraulic head and the injector nozzles are very closely mated. For protection, there are 3 filters. The primary is mounted on the vehicle frame. And the secondary and the final are mounted on the engine. The first, the primary filter, is of the multiple disc type. It must be drained daily, and even more often when conditions are bad, such as dust storms, excessive humidity, or tropical mold-making conditions. The retaining bolt may have to be loosened to allow venting of the filter case, thereby creating a free flow of fuel. This type of filter is not disposable. It must be removed, cleaned, and then reinstalled. The casing and disc element must be thoroughly cleaned to ensure the removal of even the smallest particles of foreign matter. The recommended solvent and air pressure will do the job. After cleaning, reinstall the filter casing with its element, then tighten it. New O-ring gaskets must be used. When large quantities of water are found in the primary filter, you must also drain the secondary and the final filters. The secondary and the final filters are of the cartridge element type. Each is equipped with a separate air vent to prevent air spaces or voids which might cause subsequent damage to the fuel system. Most water and foreign matter are removed from the fuel by the primary filter. The secondary and final filters will remove anything that remains. Because dirt is the primary cause of fuel injector malfunctions, these replaceable type filters must be serviced at specified intervals. The two filters are identical and have interchangeable and replaceable elements. If new filter elements are not available immediately, don't throw away the fouled ones. A used filter is a lot better than no filter at all. Clean the filters as best you can when you run into an emergency situation. However, new filters are always recommended. Large quantities of water that are found when draining the primary filter will require that you get direct support to replace the secondary and the final filter elements. Anytime a filter has been removed and replaced, the system must be purged of air. Open the bleeder valves on top of the secondary and final filters. Turn the accessory switch to on and allow the in-tank pump to fill the three filter housings. With the pump still running, open and close the bleeder valves until the air bubbles disappear. Then tighten the valves. Prior to starting, the engine must be cranked for a few seconds with the stop control knob pulled out. This is to check for hydrostatic lock. Then recheck the gear shift neutral position and start the engine. With the engine running, recheck for air bubbles at the bleeder valves. The fuel supply tank must also be checked carefully. Fuel must be kept at maximum level to minimize the condensation of moisture in the tank. Open the drain plug at least once a week to remove the sediment and condensed water. Because sediment and water settle to the bottom of the tank, you won't waste much of the fuel oil. Note the separation of eyes of water in the fuel. Oversight and carelessness will often deadline a multi-fuel engine. Let's see some typical troubles that may develop and give you their probable causes. Problem: no fuel being delivered at the fuel injector nozzles. Probable causes: defect in fuel tank pump, fuel delivery system, or the fuel lines. Problem: fuel being delivered at the injector nozzle, but engine will not start, will not run, or runs rough on one or more cylinders. Probable causes: crossed fuel lines, improperly timed fuel injector pump, defective delivery valve or spring. Problem: engine exhaust smoke is excessive and engine runs rough, sluggish acceleration. Probable cause: defective fuel injector nozzle. Another probability: injector pump improperly adjusted causing increased fuel delivery. When the engine is hard to start or runs erratically, it is likely that there are air pockets in the high pressure lines to the injection nozzles. These and many other problems and their causes are covered in your technical manual with the corrective actions. When troubleshooting, always follow a logical sequence, from the simple to the difficult. Testing and adjustments of the injector pump must only be done by qualified ordnance personnel. Shown here is the PSB-6A on the standard test stand. Seals are put on the density compensator, the governor, and the high-speed adjusting screw so that after adjustments have been made, any tampering will be obvious. The heart of the fuel system is the injector pump, which delivers to the nozzles at high pressure accurately measured quantities of fuel. Service and repair of this pump is performed at general and depot maintenance level. Let's break down the components of the PSB-6A pump to learn more about them and understand how they function. This is the pump camshaft, which is driven by the engine camshaft. It fits into the lower part of the pump housing. The advance unit is the item on the right as you look at this picture. It is mounted at the front of the pump. The advance unit is of the centrifugal mechanical type. It operates on the same principle as the governor to advance the timing of fuel injection. Engine speed causes the flyweights to swing out and force the sliding gear towards the advance unit hub. The timing, with relation to the top dead center position of the engine piston, is advanced within a given range up to a maximum of 9 degrees. This possible advancing movement of the camshaft is indicated here by hand and is visible at the governor weights. The pump housing contains the quill shaft. The quill shaft and the fuel supply pump are both driven by a worm gear on the pump camshaft. This cutaway shows it better. The quill shaft transfers rotary motion from the camshaft to the fuel plunger drive gear. Set into the top of the pump housing is the hydraulic head assembly. The hydraulic head assembly consists of the hydraulic head, the fuel delivery valve, the plunger inner spring and fuel plunger, the plunger drive gear, and the plunger sleeve. The governor is located at the rear of the pump. It is of the centrifugal mechanical type with camshaft weights. It controls fuel delivery as a function of engine speed and is driven directly from the rear of the pump camshaft without gearing. Other parts of the governor are the sliding sleeve, a fulcrum lever, and an operating shaft and lever. The governor movement is transferred to the injector pump metering device as demonstrated here. On the governor housing is mounted the fuel density compensator. This device automatically varies the quantity of fuel delivered to the engine so that the maximum power output of the engine remains constant regardless of the type of fuel being used. On this test stand, with the compensator mounted on its side, as the stop plate moves up and down, the compensator reduces the delivery of fuel when it is thick, that is, of high density. it will increase delivery when the fuel is thin or of low density. The test stand shown here is also used to calibrate the injector pump. With the aid of these drawings, we can see how the fuel is channeled through the pump and other components. From within the fuel tank, a 24-volt non-positive pump delivers the fuel under low pressure to the primary filter. From the primary filter, it goes to the main supply pump. The main supply pump is driven by the injector pump camshaft. Fuel under increased pressure flows first through the secondary filter and then through the final filter. These last two filters are of the replaceable cartridge type. The flow continues to the fuel density compensator. A sample of the fuel is passed through the compensator to determine the proper adjustment. This adjustment for fuel type is made automatically by a metering device. Excess fuel leaves the fuel injector pump through the overflow valve. The fuel injector pump pressurizes, meters, and delivers charges of fuel to the 6 injection nozzles in the pattern shown here. 1, 5, 3, 6, 2, 4. Excess fuel depressurized is routed through return lines to the fuel supply tank. This is a schematic of the hydraulic head. It shows only one high-pressure line. Each charge of the fuel is metered, pressurized, and delivered to a specific injector nozzle with extreme speed and precision. No eye could follow the action. Let's look at the action again on this sketch. In the following animation, you will see what happens inside the hydraulic head. These are the principal components: the camshaft, the quill shaft, the plunger drive gear, the fuel plunger, the plunger sleeve, the control unit, the delivery valve, and the overflow valve. The plunger is lap-fitted to a plunger sleeve located in the fuel sump. The plunger is also fitted to its bore to ensure against leakage during operation. With tolerances in the millionths of an inch, the plunger moves up and down and round and round. With each revolution of the camshaft, the plunger goes up and down 3 times and 180 degrees around. The upward movement of the fuel plunger is caused by 3 lobes on the cam. At the top of the travel, pressures on the plunger are nearly 3,000 psi. The low-pressure fuel in and fuel out passages are connected to the fuel sump. This permits the fuel to circulate, cool, and lubricate the plunger and sleeve. Fuel also enters the vertical and horizontal passages in the plunger. The intake phase of the pumping cycle begins when the plunger is at the bottom of the stroke. Fuel from the supply pump is channeled to the hydraulic head. It fills the pressure chamber above the plunger. Fuel also enters the drilled passages in the plunger and the fuel sump surrounding the plunger sleeve. The overflow valve maintains the supply pressure in the hydraulic head at 27 to 33 psi and allows excess fuel to leave the pump. To illustrate the action of the plunger, this sketch shows the plunger sleeve cut away. As the rotating plunger moves up, it passes and closes the fuel in and the outlet ports. This is the port closing position. The fuel above the plunger is trapped and ready to be pressurized. The plunger continues to move up, pressurizing the fuel. This high-pressure fuel, shown in red, opens the delivery valve. The plunger still continues up, and the fuel leaving the delivery valve moves through the communicating duct back to the plunger annulus. From the annulus, it moves up into the distributing slot and then into the high-pressure fuel line to the nozzle and into the engine cylinder. At this time, the fuel outlets in the plunger are still covered by the plunger sleeve. After sufficient upward travel of the plunger, the horizontal fuel outlet clears the top of the sleeve and becomes exposed to low pressure in the sump. This ends the pumping cycle. Beginning with the intake phase, here is how the metering function is accomplished. The plunger sleeve is moved up or down by the control unit, which is activated by the accelerator linkage and the governor action. The total movement of the plunger sleeve during actual operation is approximately 3 millimeters. The position of the plunger sleeve determines the quantity of fuel delivered per stroke of the plunger. Let's start the explanation with the plunger at the port closing position. Study this picture for a moment. The outlets of the horizontal fuel passage are now a specific distance from the top of the plunger sleeve. This distance is equal to the distance the plunger has to move to accomplish an effective stroke. When the plunger sleeve is raised, the outlets of the horizontal fuel passage remain covered until relatively late in the plunger stroke. Therefore, the effective stroke of the plunger is made longer and more fuel is delivered to the engine cylinder. If the plunger sleeve is lowered, the outlets are uncovered sooner in the delivery stroke. This makes the effective stroke shorter and allows delivery of a smaller amount of fuel. The injector pump plunger sleeve is also used to stop the engine. Pulling the hand-operated engine stop will lower the plunger sleeve. With the plunger sleeve at the extreme lower position, the fuel outlets remain exposed. Since no high pressure can be developed on top of the plunger, fuel cannot be delivered to the nozzles and the engine stops. To explain the delivery valve, it is best to see how it works in relation to the complete pumping cycle. The delivery valve is held closed by spring tension and the residual fuel pressure in the lower delivery valve fuel passage. When the plunger is down and the valve is closed, we have supply pump pressure in front of the delivery valve and residual fuel pressure at the rear of the valve. As the plunger moves up, it pressurizes the fuel, increasing the pressure at the front of the delivery valve. When the pressurized fuel exceeds the combined pressure of the residual fuel and the spring pressure, the valve will pop open. A metered amount of fuel is then forced around the valve into the distributing slot and into the line to the nozzle. At the end of the effective stroke of the plunger, the fuel outlets are exposed to low pressure. This relieves the high pressure in front of the delivery valve, causing the valve to enter its bore. As the front of the retraction piston enters the valve bore, it blocks the passage. The retraction piston then moves deeper into the valve bore until it reaches the valve seating surface. The displacement volume created by the movement of the piston lowers the pressure at the rear of the valve. This consequently reduces the residual pressure in the line. The lowered line pressure promotes rapid closing of the injector nozzle valve. To summarize, a multi-fuel engine will operate on many types of fuel. For the most efficient operation, choose either diesel fuel, compression ignition fuel, jet petroleum fuel, or low-octane gasoline in that order. The fuel density compensator automatically adjusts the quantity of fuel delivered to the engine for maximum engine power, regardless of the type of fuel being used. The system of filters is very important. Dirt, moisture, and fungus can cause plenty of trouble. Maintenance of a multi-fuel engine is no more complicated than maintenance of other types of engines. But the multi-fuel requires intelligent alertness for trouble and a real sense of responsibility. The man responsible for a multi-fuel engine must be a real pro.